Hi friends, welcome back to yet another video. Today I have a very interesting problem here to solve. So this was asked in GATE 2020. It's a 1 mark problem. It's quite an interesting problem for a couple of reasons. Reason 1, you're asked to find the natural frequency, the forcing frequency, not the natural frequency, the forcing frequency for which the amplitude of force transmitted to the ground will be F0 or what is initially applied. So there are a couple of things you should know. What is the force transmitted? What does that quantity physically mean? So first think of a thought experiment when things are not moving. Say it's a static problem. I apply here f of t, which is corresponding to f0 cos omega t. Nothing is moving. Then what will be the force transmitted here? For this problem to be a static problem, the f of t should be simply capital F0. Okay, so this is the static problem where I mean to say that the force doesn't change with respect to time. Then this problem is a static problem. Then the force transmitted to the ground will be simply F0 because that is how statics work. Whatever force you apply here, it gets transmitted to here. Concept number 1 is in dynamics, when f of t is f0 cos omega t, now depending upon the time instant, the force acting on this mass varies. So the whole system is set into motion. It starts moving. Then the force transmitted to the ground will be no longer f of t. Okay, so this is the concept. So if it's a static problem, the force transmitted will be equal to the force that we applied over here, corresponding to this case. But the moment the dynamics sets in, the force transmitted is different. Now till this time I was explaining in words. Now let's go ahead and have a look at the maths behind it, or the mathematical model that governs the system. So here I have shown you a single degree of freedom system. It has only 1 degree of freedom. The motion is denoted by little x. So the governing equation is pretty straightforward. Mx double dot plus cx dot plus kx equal to f of t. Then I am assuming that f of t is equal to f0 e raised I omega t. So at least a few of you might be thinking in mind, see in the question the force is given as f0 cos omega t. Then why you are taking the excitation force as f0 e raised I omega t? The reason is pretty simple, because f0 cos omega t can be written as the real part of f of t. So this is the force given in the question, that's why I denoted it as f underscore q. Clear? And the algebra becomes much easier when I have the excitation function in this form. Clear? Now let's go ahead and solve this problem. It's pretty simple. This corresponds to harmonic excitation, where the frequency of excitation is capital omega. I can assume my response to vary like this. And one very important thing to remind or remember is this: you have your little x varying like this, and where your capital X is your complex amplitude. It contains the phase information also, not just the amplitude information, but it contains the phase information also. This is a very key concept that often students try to overlook. When you go to a Viva and you have a very good professor, he can really trouble you with all these kind of questions. So whenever you assume this step, be clear that this is a complex amplitude. It contains both phase information as well as the amplitude information. Good to go. Now rest of the things are simply plug and check. Once you do this exercise, you get an expression for the amplitude of the response, but your job is not done. You're not asked to find the response or the amplitude of the response. You're asked to find out what is the amplitude of the force transmitted. Now, how you will compute the force transmitted? For that, let's have a look at the diagram once again. See, here you have the ground, here you have the ground. So at any point of time, the force transmitted to the ground will be the sum of forces acting through the spring as well as through the damper, whatever you call it. This is a dashboard or whatever you call it. I will call it a dashboard. So whatever is the force transmitted to the ground will be the sum of forces in the spring plus the force acting in the dashboard. Clear? For a static case, for a static scenario, when your f of t was simply f0, there is no force acting through the dashboard, because the force acting or the resistance offered by the dashboard varies like this: cx dot. As you are applying a static force, there is no x dot because velocity is 0. Then there is only spring force in the problem, and spring force is simply k times your x, which is equal to the, where x is the displacement, and it is equal to the externally applied force. But once the system starts moving because of this kind of an excitation, then there is an additional term. There is an additional term or additional contribution to the force transmitted from the dashboard. So that will be simply, now FTR will be kx will be there, plus cx dot, because that is the force coming from the dashboard. So for a static case, you had only this term, but when you have the system moving, you will have both these terms. So this is the expression for force transmitted to the ground when the system is moving. Now let's go ahead and evaluate what is the amplitude of that force transmitted. It's fairly easy because we have covered all the steps. See, I could have simply taken the formula for force transmitted and explained you all these things, but I don't want to do that because I would like to drive home certain basic concepts which will help you to stamp certain things in your head, and it will help you down the line once you start working as an engineer or anyone. So so force transmitted is this one. Now I can substitute for little x like this, then I can arrive at another expression for force transmitted. It's simply plug and check. Now I am asked to find out what is the magnitude of this quantity. Just remember or just have a look at this expression and understand that this is also varying with respect to time. Okay, it is also varying sinusoidally, but you're asked to compute just the amplitude. So the force transmitter will be taking a shape like this. This will be the curve for force transmitter with respect to time. So you're asked to compute the amplitude. This is the amplitude. Okay, so in order to evaluate the magnitude or amplitude of the force transmitted, you just need to take the magnitude of these two complex numbers. We have already evaluated the expression for capital X. Plug that here. Again, simply plug and check. A bit of complex algebra will help you here. Now the ratio of force transmitted to the initial force what you are given, the F0 was the amplitude of the initial force what you have applied or what you have given as an input to the system. It comes out like this. Then again some simple mathematical manipulations to give a feel. So I am trying to divide both denominator and numerator by k, and I am trying to bring in the substitution for c omega by k. So here couple of things. Zeta is our damping ratio, very normally used in engineering calculations. It is sometimes we use values like 0.02 and all, but that is of no interest in this problem. But zeta is a damping ratio. Then we have another constant we are introducing now, little r is the frequency ratio. It is a ratio of your forcing frequency to that of the natural frequency of the system. Make sense? to zeta r. Now bringing in these two things, the expression for the transmissibility ratio or the ratio of force transmitted to the initial excitation force will assume this form. Clear? Now they are asking you in the question, you have to read the question very clearly and very carefully. They are asking you for what value of omega, for what value of frequency does the force transmitted is equal to F0. That means this whole ratio goes to 1, or in other words, both the numerator and the denominator are the same, isn't it? 1 means 1 by 1. That means both the denominator and numerator are 1 and the same. For both numerator and denominator to be same, a good solution is, or a possible case is, r square is equal to 2. What happens when r square is equal to 2? Here if you plug in r square is equal to 2, then you will get minus 1 whole square, that is again 1. So both denominator and numerator will be the same quantity, which in turn means that this ratio is 1, or in other words, the transmitted force is exactly equal to F0. So r square equal to 2 will meet this criterion. R square is equal to 2 in turn means that r is root 2 and omega by omega n is equal to root 2, and omega is the forcing frequency is root 2 times 2 root of k by m. This is the ratio. Clear? So at this value of forcing frequency, the force transmitted to the initial force will be same, or in fact both of them will be same, and the ratio will be 1. Clear? Before we wind up, I thought it would be perfect to show you the curve, how this transmissibility ratio varies with respect to the ratio of forcing frequency to that of the natural frequency. This is the little r that I was talking about in the video, and this is same as the force transmitted to F0 that I was talking about in the video. So a couple of observations. The first one, for a value corresponding to omega by omega n is equal to root 2, or it will amount to something like little r is equal to 1.4, somewhat like that. So for a value corresponding to that, you see, irrespective of the damping present in the system, your transmissibility ratio is always 1. And prior to that, you see, you provide more damping, it tries to bring down the transmissibility ratio, but as you cross this value over here, smaller the damping, smaller the transmissibility ratio. So these are a few observations that will come handy in knowing more about this kind of curves. One final thing, it may cause a bit of confusion, but it's worth discussing. In two textbooks, in Mirovich as well as S.S. Rao, they have given different expressions for force transmissibility. And they have different curves for displacement transmissibility in the two tests, one in S.S. Rao and the other in S. Mirovich. So I think the best way to answer, whenever you try to answer this kind of question, is try to draw the free body diagram, try to solve on your own and then answer it, rather than just simply mugging up things. So whenever you are asked something regarding the force transmissibility ratio, it is always better to draw the free body diagram and then reach the final answer. And I think whatever is given in S.S. Rao textbook sounds more logical to me when you are drawing the force transmissibility curve. So this is the displacement transmissibility curve what I have shown here, but this is same as the force transmissibility curve for the system in our question, but this is not the force transmissibility curve for this system. For this system, it is given in S.S. Rao, so kindly have a look. Maybe I would have caused a little bit of doubt towards the fag end of the video, but the key takeaway is that force transmitted is a concept that you need to really understand. It is different from the force what you are given to the system. and there is an augmentation in that value as you when your system is vibrating or when your system is undergoing some kind of motion. So makes sense. And the last bit what I wanted to convey is this: the force transmissibility curves, you need to be extremely careful. You need to think of the system. You cannot mug up certain curves, certain equations, and go out there. You try to draw the free body diagram, then arrive at an expression for this, and try to read the SS Rao textbook a little bit, especially on this subject. Thank you.